good. Second talk by Ludovic. I think we're a few minutes early still. So actually, just 2 minutes. We might as well.
Hi again. It's been a while. So now we're going to be talking about spectral method and community detection. So very roughly, what's community detection? It's just the task of finding community structure inside the real-world networks. For example, we want to find both blue and red partition inside the given graph. And in order to study the performance of algorithms for this task, a model was created, which is the stochastic block model. It's a generative model for such community-based graphs, and is simply a graph on n vertices to which we assign community labels, sigma, that are uniformly chosen in some set number of communities, say R. And then we construct a random graph whose edges are all independent, and the probability of presence of an edge simply depends on the community memberships of its endpoints. So here we will study sparse block models. So the probability of an edge being present is some constant over n, where the constant are drawn from a fixed symmetric matrix W. And the goal is observing the graph G with community labels mask to recover these memberships as well as we can. A wide array of methods has been designed for this, but we will study specifically the spectral methods, whose main idea is to find a matrix associated with G, which is usually taken to be the adjacency matrix. And when the signal is strong enough, which means that the average degree and the difference between communities are large enough, then the top eigenvectors of this matrix M will be correlated enough with the community structure to recover some labels. And the rest of the eigenvalues are confined in a bulk similar to the Wagner semicircle law. The problem is, in our case, that when we have sparse random graphs, there is not enough signal for the adjacency matrix to work. So we had to find other methods and other matrices to perform this task, mainly the self-avoiding matrix from Laurent Massoulier, a matrix that counts non-backtracking paths in Mossel and al., or the non-backtracking matrix, which is a little different, mainly introduced in Xakala and al. But both have some caveats. All have some caveats. Some require that there are only two communities, and the non-backtracking matrix requires a weird asymmetry condition on the eigenvalues of the connectivity matrix. And all those methods also only work under the so-called Kesten-Stigum threshold, which is the threshold on the eigenvalues of W that's required for almost every method to work. So in order to tackle this problem, we introduced a new matrix defined with a parameter L, and we define it by simply it is 1 if and only if the distance between both vertices is L and it's 0 otherwise. So it's somewhat a generalization of the adjacency matrix when L is larger than 1. And we showed that under the Kesten-Stigum condition, when L is taken to be growing with log n with a small constant times log n, then the matrix DL exhibits the required spectral structure that we described previously. And this is under absolutely no condition other than the Kesten-Stigum threshold. So it works under any number of communities and under any form for W. And indeed, we see when we look at the eigenvalues and eigenvectors for M, for D, that there is a bulk which is not circular anymore, but there is still a bulk, and some eigenvalues outside of this bulk. And if we scatterplot the second and third eigenvalues and reveal the community labels, we see that they are actually pretty well clustered, and any decent clustering algorithm will manage to capture at least a fraction of the communities. Another problem that is interesting in the study of stochastic block models is the robustness of the methods, because in real life, the real life networks we see are not exactly like the model that generated ones, and they tend to have a lot more small clicks are small, dense subgraph that are mostly independent from the community structure. So a good way to study the performance of models under those real-life networks is to study the robustness of the algorithm under adversarial perturbations. So we define an adversary that when given a stochastic block model graph G can add and remove edges at will as long as at most gamma vertices are affected, which means that at most gamma vertices can be endpoints of added and removed edges. So for example, if we had a clique, we can have the clique of size of with the number gamma squared of edges. And the problem is that in the proofs of many spectral methods, they use pretty specific properties of stochastic block models and some tree structure inside those graphs that are extremely sensitive to the addition and removal of edges. So those methods tend to fail when we add even cliques of size log n. They tend to already fail. However, the matrix DL is sparser than those, which means that it has more zero coefficients. And even when it has non-zero coefficients, they are lower than the other matrices. And so our hope was that it would be indeed less sensitive to noise. And we showed that it is the case because when we take L again to be constant times log n, then the spectral structure of DL that we mentioned that's useful for community recovery is preserved as long as we affect at most tau to the nth power edges, where tau is the what we call the signal-to-noise ratio, so it's related to the Keston-Stigum threshold. And since tau is larger than 1, we see that we can allow perturbation of size n to the epsilon. For epsilon, unfortunately, approaching 0 as we near the Keston-Stigum threshold, since tau will go to 1 as we near the threshold. So how does this compare to other community detection methods? Well, the commonly used method for robustness is the semi-definite programming methods, where we simply relax the max likelihood method into an optimization problem. And indeed, these methods are known to be extremely stable because they can allow perturbation that they can allow to add or remove n edges. So that's still a lot more than our algorithm does. But however, they are known to be pretty slow, while the algorithm based on the matrix DL, which just applies some clustering algorithm to the top eigenvectors of the matrix, can run in almost linear time, so n to the 13 over 12, which is pretty fast compared to SDP methods. And additionally, no SDP methods can reliably reach the Keston-Stigum threshold. So some miss it by a large constant, some require some specific structure in W, or some simply try to approach the Keston-Stigum threshold as the average degree of the graph increases, but none can actually completely reach it. So our algorithm tends to be more general. Thanks, everyone.